So what I neglected to mention on that 6.02 times 10 to the 23rd is what it's called. It's called Avogadro's number. 6.02 times 10 to the 23rd. And again, I'll put particles. 6.02 times 10 to the 23rd is Avogadro's number. Now, how big is Avogadro's number? It's ridiculously large. When you start to think about how big it is, here's a couple of examples. If I had Avogadro's number, 6.02 times 10 to the 23rd, number of soft drink cans, that would cover the surface of the Earth, 6.02, the entire surface of the Earth, to a depth of over 200 miles. Ridiculous number. If you spread that many, 6.02 times 10 to the 23rd, number of unpopped popcorn kernels across just the US, a popcorn kernel, the entire country, the entire United States would be covered in popcorn to a depth of over 9 miles. Think about how many popcorns you would have to get to 1 mile over the entire United States. Ridiculous number. If you are able to count atoms at a rate of 10 million per second, so 1, 2, 3, 4, up to 10 million in 1 second, it would take about 2 billion years to count the atoms in 1 mole. Ridiculous number. So again, here's an example. Here's another one. If you have 6.02 times 10 to the 23rd dollars, it's a lot of money. If you spend this rate of $1 billion per second, so here's $1 billion, here's $1 billion, here's $1 billion, how long would it last? Well, think about it, okay? I'm spending $1 billion in a second, all right? How many years would it take me per second, etc., etc.? A second in minutes, minutes per hours, hours in a day, 365 days in a year. How many years would it last? Well, there's a little calculation, and again, I didn't make this up, but let's take a look at what this is. USDSB.on.Canada. It's a Canadian organization. So this many dollars, spend it at a rate of $1 billion per second. How long would it last? Here's the solution. It would take 19 million years, 19 million years if you spent it $1 billion a day, $1 billion a second, and it would still take 19 million years. Again, if you haven't figured out that this is a ridiculously large number, hopefully you can see that. I also found a little song on the web, and I think it's pretty cool. It's kind of catchy. It's a catchy little tune. And this is it's a mole as a unit. It's on YouTube. This is Mad Penguin Films. Let's go ahead and just play it.
In the ground, or a spot on your chin that you gotta shave around. But there's another kind of mole of interest to me. That's the kind of mole they use in chemistry. A mole is a unit, or have you heard, containing 6 times 10 to the 23rd. That's a 6 with 23 zeros at the end. Much too big a number to comprehend. Now say you had a mole of pennies to distribute round the world. Give to each of the 5 billion grown-ups, boys and girls. There wouldn't be a single soul down and out of luck, 'cause everybody in the world would get $1 trillion. Or say you had a mole of paper and stacked it toward the sky. Paper's awful thin, but that pile would get so high, it'd reach up into outer space. In fact, I think you'd find it'd go up to the moon and back 80 billion times. And a mole is a unit, well, have you heard, containing 6 times 10 to the 23rd. That's a 6 with 23 zeros at the end. Much too big a number to comprehend. Now suppose a bowl of marshmallows fell upon the planet. Over each square inch of land and sea, you think that you could stand it? That layer would be 12 miles high and of course block out the sun. We're talking close to 5 million trillion tons. Well, maybe we could save ourselves if we all started eating one marshmallow each second. Not two, because that'd be cheating. With 5 billion people munching, how long do you think it'd take? 40 million years, and that's without a bathroom break. And the mole is a unit, or have you heard, containing 6 times 10 to the 23rd. That's a 6 with 23 zeros at the end. Much too big a number to comprehend. But say you had a mole of atoms, would the pile be immense? Should I say the answer now or leave you in suspense? Well, atoms are so very, very small, you understand. You could hold a mole of atoms in the palm of your hand. So shake a little sugar in the middle of your palm. Now you don't want to spill it, so try and stay calm. You hardly can imagine and barely realize there are more atoms in that sugar than stars up in the sky. And the mole is a unit, or have you heard, containing 6 times 10 to the 23rd. That's a 6 with 23 zeros at the end. Much too big a number to comprehend.
All right. So some serious props for these guys. I think it's a pretty cool little video song. But that's the mole. I mean, the mole is ridiculously large. 6.02 times 10 to the 23rd. I want you to recognize, though, that they did mention, as big as that is, I'm holding a mole of water right now. So as big as that is, I'm still holding a mole of water, not very heavy. How do I know I'm holding a mole of water? Well, again, I have 18 grams. 18 grams of water is 1 mole. 1 mole is 6.02 times 10 to the 23rd particles. There you are. So if I've got 18 grams, which density of water is 1 gram per milliliter, if I've got 18 milliliters, I've got 18 grams. Therefore, I have 1 mole. 1 mole is 6.02 times 10 to the 23rd. So that's a great way of looking at Avogadro's number.